Hi to all, how's it going? I hope you all doing really well. I would like to start this video by introducing a relatively new development brought to us by Abdullah, the coder of the Sketcher workbench, and then further improved by realthunder in LinkStage3. And this is the ability to export from the Sketcher and use partial geometry of sketches. This technique can become a huge time saver in certain workflows where we need to model, for example, ribs or other intersecting geometry. So just to have an idea of how things work, let's open the sketch, and while at least having a vague idea of what we want to model, let's start drawing some ribs geometry. So notice how I haven't bothered to construct a clear outline of our ribs, and I've only used simple rectangles to create an outline. So to use this new feature there are basically two ways. One is inside the Sketcher and one it is inside the part design workbench. Let's start first with the Sketcher way. We can select some geometry that we're interested in. Then we can use these two tools here, and they are export the selected geometry as separate child objects, and this will create 4 different sub sketches for the 4 geometry selected. Or we can use the export selected geometry as one single child object, and this will create a sub sketch, as we will see in just a second, containing only the selected geometry. So let's try this. And you can see that we have an export here. We can go ahead and make exports of random geometry that we're interested in. And these new sketches can be opened independently. Let's close our sketch, and then selecting the exports we can do our paths. Select our second export, do a path, and we will hit an error. This is because I forgotten to select an edge so that the wire was fully closed. Let's cancel our path, reopen the export, and if we take a closer look here, I have missed this small edge here, so I will delete my export, close the sketch, delete this export, reopen the original sketch, the master sketch, and I will carefully select the geometry that I'm interested in. Let's export again, close the sketch, select the export, do a pad, we'll do again the 5mm one, and I think that this was our third export, so do a pad again, or 3mm, and we have our ribs using the sketch export tool. Notice how the Sketcher technique export part of our sketch and we have a reference. There is still another way to achieve the same result using directly the part design workbench. So if we go back and delete everything here, we have our sketch. Let's switch to wireframe. If I select geometry directly in the part design workbench while outside of the edit sketch mode, and hit pad, we will achieve just the same result. How cool is this? So let's try with 5mm, hit OK. This second technique is an automatic way of exporting part of the sketch, but it uses shape binders instead of sketch exports to reference the desired geometry. So let's try to achieve exactly the same result as before using only the part design workbench. So if I switch back to wireframe, switch back to shadow mode, and we have exactly the same result with different paths using arbitrary geometry from a single sketch. Another thing that was pointed to me by Leandro Hack in the comments under the last video is why I didn't use the hole feature for creating the holes for the screw in the bottom side of the case. So I will quickly show how this tool works, because it is really useful and a lot faster than the method that we previously used to make the holes. So we will select the circles that create the pads for the screw holder and hit the hole tool in the part design workbench. Let's make it a little bit bigger. I want my profile to be an isometric. I want a M2.5 screw. I also want a counterbore hole cut and the depth of 2 millimeters. Of course, I want it reversed, and if we take a look at our cut here, in less than 10 seconds we have a perfect cut for an M2.5 screw. So with this new techniques under our belt, let's go ahead and do some finishing touches on the top part of our case. One thing that I don't like is how our rib here doesn't touch the top face of our case. So to correct that, we need to activate the top part. We need to hunt down the sketch that creates the rib, and it should be a pad somewhere in here. So it is this pad. Let's expand it, unhide the sketch, hide for just a little bit that top element, so we can clearly see the sketch, and we see that it is comprised of two different elements. I will select these edges here that I'm interested in, unhide the chamfer, and let's do a pad. A pad will be created. I want it to be up to face. Select the face, and just like that, with the modified the geometry, we're using only part of a previously created sketch. I would like to use this example to praise the incredible work that realthunder has done on the new toponaming algorithm. So just to explain, this kind of major modifications to the previous history of the geometry will always create problems, because we have a lot of cross references between the top side of the case and the side door. As you can see, if we go into the history of the side door, we have an error message, and this is a missing external geometry reference. This happens because the whole geometry of the top side of the case is different from what it was previously. But in this iteration of LinkStage3, and I wanted just to remember everybody that this is trickling down into the master now, thanks to great efforts from the developers. Now, just by confirming the path and letting FreeCAD do its magic, the new toponaming algorithm will correct, or at least do its best to correct the errors that come after it. In my opinion, this is really a game changer for FreeCAD. I will model now some sort of support here for our door in order for it to not fall down inside the case, and then we will take on a quick assembly of our components. So for the purpose of this tutorial, I think that the modeling part is done. Let's move on to the assembly. Assembly, and assembly free in particular, is a huge and complex topic. My intention here is to do a light tutorial while doing my best to explain some basic concepts of assembly free. We will do an assembly in a separate file, and the first thing that I need to explain is the concept of link. A link type object in the context of this assembly is an object that often does not have geometry data of its own, but instead links to other objects for geometry data sharing. This is the most efficient way of duplicating the same object in different places with optional scale, mirror, and material override. You can see it as a clone of previously modeled geometry. For this example, I want to create my assembly in a separate file, so I'll go ahead and create a new file, rename it as Raspberry Pi 2 assembly, and we will create links that will reference the bottom, top and side door geometry of our case. While working with multiple documents, FreeCAD gives us the possibility to have different display modes for the tree view. This can be tweaked using this drop-down menu, and we are interested in having a multi-document view. Of course, you can have single document. This will make so that the tree view will display the tree history of the selected document. But now we are interested in seeing a multi-document tree view. Creating links across documents can be a little bit tricky at the beginning, but bear with me. And let's go ahead and select the geometry of the bottom body. Then, while holding down the Control key, right click on the Raspberry Pi 2 assembly file, link action, and make a link. This has created a link of our bottom side of the case inside the Raspberry Pi 2 assembly file. Again, in the first file, select the top geometry, hold down the Control key while right-clicking on the Raspberry Pi 2 assembly file, link action, and make a new link. Select the side door in the first file, move the cursor over the name of the second file, hold down Control, right-click, link actions, and make a new link. Select the 4 screws, move the cursor over the name of the second file, hold down Control, then right-click, link action, and make links. We still need a link for our pi geometry, so select the pi geometry, move over the name of the second file, hold down Control, right click, link actions, and make link. Now that we have our geometry imported, we can use this drop down menu and use the single document mode for a cleaner tree view. And we will move to the assembly-free workbench. In order to create an assembly, of course, we need to first create a new assembly container. We can rename it as Pi2 assembly, and selecting all of our previously made links, we will drag them inside the assembly container. Let's expand the tree view. And you will see that an assembly container has 3 main branches. It has parts, elements, and shortly we'll have constraints also. The assembly container will group the imported geometry under the parts tree structure and will create new tree voices for the elements that we will use to create our assembly. At the moment we have some free floating geometry inside our assembly, and we can use the mover tools to move it around by selecting different elements. So if for example I select the top link, the link for the top part of our geometry, and use the axial move, we can freely move our geometry. The same with the side escape to dismiss the tool, the same with all the other elements in our assembly. An important note, the mover tools of assembly 3 are different from the right click menu transform in the tree view. The mover tools of assembly 3 will take into account the constraints that we will be setting. So while working with assemblies, use always the mover tools inside the assembly 3 workbench. Notice how I have other 2 tools active, and these are Auto Recompute and Smart Recompute to save on computational time. Because we have all of our geometry free floating into space, we are interested in setting some base for our assembly. To do this, we will select perhaps the bottom face of our case and use the locked constraint. The tooltips in LinkStage3 are really well made and can give a lot of information of what the tool does and its properties, so try to always give a good read to the tooltips. Creating our first constraint will also create a new branch in our tree structure. This branch will hold the name of our constraint, and the constraint has some elements to it. Constraints and elements have properties that can be modified. Elements can be considered a connection interface of the owner assembly, so that other parent assemblies or geometry can know which part of this assembly can be joined with others. In this particular case, we have only one element, which is the starting point of our assembly. With our first element fixed into place, it is now time to start constraining the other components. And we will start with the screws. Let's hide our element. Select the screws one by one, and let's move them slightly out of the way. Escape to dismiss the tool. And as a general rule of thumb, you want to select first the geometry that you want to stay in place, then the geometry that you want to move, and apply the desired constraint. Generally, when you know that your components are kind of fixed into place, it is advisable to use the attachment constraint, because it is the least intensive computationally, and this can mean a big difference while working with kind of complex assemblies. Let's use the attachment constraint, and you see that our screw has moved into place. If we now select our screw and use the mover tool, it can be moved from its place. Hit escape to dismiss the tool, and I will do the same with the other 4 screws. Notice how in the case of the attachment constraints we have 2 elements. The first element is the first edge that we've selected, and the second element is the second edge that we've selected on the screw. This will come really handy later in the video for manipulating the position of the geometry. So now let's move on to the next element that we want to fix into place. Hide the top side of the case, hide the door, and if I select the Pi 2 part container and use the mover tool, I can move it slightly out of the way. Escape to dismiss the tool. Let's select an edge on the bottom side of the case, then select the edge, the corresponding edge that we want to match on the Pi geometry, and use the attachment tool. The geometry was snapped into place using the local coordinate system of our selection. Bear in mind that we are manipulating a whole part container, but referencing geometry from somewhere inside all this tree structure. Of course, that geometry that we've referenced has its own coordinate system. Here we will see the power of using elements as a mean to connect geometry. So if we go into our last constraint, expand the tree view, select the second element, which is the edge on the Pi geometry, right click on the tree view on that element, and we will just flip element. This will make so that the Z direction of the corresponding element to be flipped. So magically our case has fallen into place. Again, we can select the part container of the Pi board, and using the mover tool control that it is indeed fixed in place, and we can't move it anymore. Escape to dismiss the tool, and let's move on. The next thing that we want to attach is the top side of our case. Let's see where we want to attach it, and I think that I want to use this edge on the main board of the Pi. Then we will select this edge on the top case and use the attachment constraint. And see how there is something that just isn't right. This geometry is intersecting. If you followed the previous tutorials, you might remember that while constructing the geometry of the screw legs here, this one here, we have given an offset of, if I remember correctly, 0.2 millimeters from the mainboard geometry. While doing this, the assembly, that offset will create this kind of mismatch, because it tries to mesh the geometry just like in real life. To remedy to this, we can select the last attachment. Let's expand the tree view, and by selecting the last element, we can give it an offset in the Z direction by 0.2 millimeters. 0.2 millimeters. And now our case follows the contour of the cut, while having this 0.2 millimeters offset from the board and the screw leg here. So let's unhide the geometry of our side door, and in order to fix the side door to our top case geometry, we will use the plane coincident constraint. This will fix two planes together, matching in the center of them. We will first select some geometry on the top side of the case, which is the geometry that we intend to stay fixed, and I will select this face. Then I will select this face here on the side door, and I will use the plane coincident constraint. This will make so that the side door will snap into place, matching the center of the two planes that we've selected previously. If we inspect our geometry, you can see that the geometry was matched without any tolerance. We will expand the plane coincident tree, select the second element perhaps, and we will give it an offset in the Z direction, 0.25 millimeters. And this way we have it centered on these knobs here. If we now select our side door and use the mover tool, we can check if our constraints behave correctly. Escape to dismiss the tool. When doing constraints, it is always helpful to have the pieces perhaps moved out of the way, but closer as possible to the final position that the constraint is intending. So, for example, if I select the side door and I use the mover tool, I will try to move it as close as possible to a neutral position. Escape to dismiss the tool. And as a last touch, I will select this edge here and this edge here, and we will use the angle constraint. This will create an angle constraint that has two elements, and these are the two edges. And if I select the angle constraint and give it an 180-degree value, you see that our side door snaps into place perfectly. This angle can be modified, but in small steps in order for the solver to not get confused. So for example, if I give it an 160-degree value, you see that the door is slowly opening. And let's check with a 90 degrees value to see if we don't have some collision between geometry. And I'm pretty satisfied with the result. It is worth mentioning that from this moment on our assembly has 0 degrees of freedom. If we try to select our side door and use the mover tool, it won't permit any movement, because we have an angle constraint between these two edges, which represents the angle of the opening of the side door. To modify the position of the side door, we just select the angle constraint and we choose an arbitrary angle. Okay, ladies and gentlemen, this should sum up this long series of tutorials. I really hope that you are all excited as me about the bright future of FreeCAD. There are a lot of tools that I really love, and workflows become always faster. Thank you so much for staying till the end, and I'll see you in the next one.